In this video, we're going to give a definition of the splitting field of a polynomial. And actually, there's something missing from the title, but I didn't want to make the title any longer. Really, the title should say the splitting field of a polynomial over a smaller field. Because as we will see, what we decide is the splitting field of a certain polynomial is going to depend upon what we take as our base field. I'm going to start with an example. So the example is, let p of x equal x cubed minus 2, and this is a polynomial in q adjoin x. We're later going to consider it as a polynomial in r adjoin x, that is a polynomial over real numbers rather than over rational numbers, but we'll do that later. Alright, so the question I'm going to ask is, how much must I extend q for this polynomial to split into linear factors? In other words, to factor completely into linear factors. So first, just a quick observation. Because the lead coefficient is 1, and the remaining coefficients in that order are 0, 0, and -2, we know that this polynomial is Eisenstein for p equals 2. It is Eisenstein for p equals 2, since the remaining non-lead coefficients are 0, 0, and -2, and -2 is not divisible by 2 squared, but all of those are divisible by 2, except for the lead. Therefore, this polynomial is irreducible over q. And therefore, I could extend q to include a root of this polynomial by taking q adjoin x, so taking this polynomial ring, and taking a quotient by the ideal generated by this polynomial. Because this polynomial is irreducible, it generates a maximal ideal. Therefore, the quotient by that ideal would be a field. I'm actually going to do something a little bit different. I'm just going to say, let's imagine the field of rational numbers, q, sitting inside a much larger field that I actually happen to know quite a bit about. And that's the field of complex numbers. And we're just going to adjoin something that we know is a root of this polynomial. And that's going to be the cube root of 2. So we're going to extend q by adjoining the cube root of 2, and that will give us a root of this polynomial. Alright, so let's go on and do that. So consider q adjoin the cube root of 2. And that's going to be the set of all a plus b cube root of 2 plus c cube root of 4, that's the cube root of 2 squared, where a, b, and c are rational. How do I know? I know that this is what this extension looks like because this is isomorphic to q adjoin x modulo the ideal generated by x cubed minus 2. We proved that in one of the previous videos, that adjoining this way by taking a quotient is isomorphic to adjoining by just tacking on something in a larger field that we know is a root. And we know from our previous work that this extension, because we're modding out by a cubic polynomial, it's a vector space over q of dimension 3. Therefore, we need 3 free parameters here, one for the unit 1, one for the cube root of 2, and one for the cube root of 2 squared. Okay, and I know that that looks a little gruesome, but we're not going to need to engage with this very intensely to figure out the key thing that we need to figure out in order to answer this question here. All that we need to observe here is that everything here is a real number. And I know that the roots of this polynomial by de Moivre's theorem, taken in the complex plane, so this is my real axis, this is my imaginary axis, I know that the roots of this polynomial are the vertices of an equilateral triangle, one at the cube root of 2, and then one over here, and one down here, and these are respectively the cube root of 2 times cis of 2 pi over 3, and this is cube root of 2 cis of 4 pi over 3. Okay, so those are my other two roots. And the main thing I need to see here, I'm trying to answer the question, how much I have to extend q in order for this polynomial to split into linear factors. And I know that at this point I can certainly split p of x into x minus the cube root of 2 times some other factor. And I'm going to use what I know about factoring a difference of cubes to get the other factor. That's going to be x squared plus cube root of 2 times x plus the cube root of 4. That's going to be the other factor. There I'm using the fact that a cubed minus b cubed equals a minus b, a squared plus ab plus b squared. That's what's in use there. Okay, so the question is now, have I already created a field big enough to split this other polynomial factor? If so, then I have found a splitting field for x cubed minus 2. If not, then I need to work a little bit harder. And at this point, I'm going to use the fact that the remaining roots of this polynomial, they're not even real numbers. And everything that in my current extension field is a real number. So I am going to have to extend at least one more time in order to get a field that contains all of the roots. So now I'm going to take my new field, q adjoin the cube root of 2. I'm just going to make a little diagram over here. Q adjoin cube root of 2 over q. And that extension has degree 3. We'll learn a little bit more about that notation and how it's used later. I'm also going to mark this extension in this picture over on the right. So if I draw a field just big enough to contain q and the cube root of 2, then that's what it means when I take q and adjoin the cube root of 2. I want to take the smallest subfield of the complex numbers that contains both the rationals and the cube root of 2. Okay, so now we're going to extend this field one more time. So this second polynomial factor will split. And the way that we'll do that is by just going ahead and adjoining one of the other roots. So we will now consider, switch colors here, consider q adjoin the cube root of 2 and cube root of 2 cis of 120 degrees, or sorry, I guess I was using radians earlier, so let's remain consistent there. Cis of 2 pi over 3. There we go. Okay, so this is a new extension field. It contains the cube root of 2 and also contains this. We don't know whether it contains this or not, but we're going to show very shortly that it does. In this field, we have p of x equals, same factor as before, x minus cube root of 2, times, and then this other factor, what's it going to factor into? Well, I claim that it's going to factor into x minus cube root of 2 cis of 2 pi over 3. And then the other factor is going to be x minus cube root of 2 cis of 4 pi over 3. I claim that those will be the two factors. And here's how I know that that's the case. I know that those are going to be the two factors because I know that these two elements here, those have to be the two roots of this quadratic here because they are roots of p of x and they're not roots of this linear polynomial here. Therefore, these do have to be the roots of this polynomial. And then once I know that, the only thing that's left is to show that they have the same lead coefficient. Well, this has a lead coefficient of 1, and the product of these will have a lead coefficient of 1, that is, it will start with x squared. So these have to be the same quadratic. And that's because the only way for two monic quadratic polynomials, monic meaning lead coefficient is 1, the only way for those to have the same pair of roots is for them to be exactly the same quadratic polynomial. Okay, so now I have a field in which p of x splits completely into linear factors. So what I have here, this q adjoin the cube root of 2 and this other cube root of 2, this is called the splitting field of x cubed minus 2 over q. Now remember I said earlier we were going to show that that base field is important when we think about the splitting field. And the reason is when we talk about a splitting field, we don't just mean that the entire polynomial splits into linear factors in that field. We mean something a little bit more. So here's a definition. So let f be a field, and let p of x be a polynomial in f adjoin x. I am not requiring that p of x be irreducible. It may be reducible over f. That's fine. The splitting field of p of x over f, that's defined to be the smallest extension field of f. So let's call that E, the smallest extension E of f, for which p of x factors entirely into linear polynomials, into linear factors in E adjoin X, in that new extended polynomial ring. Okay, so E is the smallest extension of F over which P of X factors completely into linears. Okay, so in other words, if P of X factors into, and I'm going to leave the possibility of some coefficient here from F, so that may be 1 or it may be something other than 1, U times X minus A1, X minus A2, and so on up to X minus AN in some extension field K, which may be bigger than necessary, then the splitting field is E, and that's equal to F adjoin A1, A2 up through AN, because that is by definition the smallest extension of F, containing A1, A2 through AN, as well as everything from F. Okay, now that should give you a little bit of pause, because if I'm taking that to be my definition, then one thing that should follow here is that this splitting field here that we came up with, let's call that E for just a moment. Well, that means E should be equal to Q adjoin the cube root of 2, the cube root of 2 cis 2 pi over 3, and the cube root of 2 cis of 4 pi over 3. And I said earlier that my splitting field is just Q adjoin these two elements. So what gives? Why the discrepancy? Well, there's actually no discrepancy here, because if we're thinking about the smallest extension of Q that contains all three of these dudes here, well, that's this. We know that Q adjoin cube root of 2 wasn't big enough to contain these two roots, because these two roots were not even real, and everything in Q adjoin cube root of 2 was real. But once we extend it again, we extend this one complex root here, this non-real root, and once we have that, P of X factors entirely. And I realize that my argument for that was a little bit sketchy, but try multiplying these out. Like, actually calculate cis of 2 pi over 3, calculate cis of 4 pi over 3, and multiply these out and see if you don't get x cubed minus 2. You actually will. So this extension is large enough, and it's just large enough to contain all three of these. Therefore, this is exactly the same thing as this. A good analogy would be you have like x squared minus 5, and you're looking for a splitting field over Q for that polynomial. It'd be like saying, well, that splitting field should be Q adjoin root 5 and negative root 5. But I mean, come on, once you do this, once you adjoin the square root of 5, you automatically have the negative square root of 5. So it's kind of the same thing going on notationally. It's just this is extra at this point. Okay, now I promised we would look at one other scenario here with a different base field. So let's zoom way out. Whoa, okay, there we go. And this time, let's take the base field. I'm going to switch colors here. Let's take the base field to be something rather larger. So let's take the base field to be the field of real numbers. So what is the splitting field of x cubed minus 2 over r? Okay, well, let's just do a sanity check here and make sure that we don't already have a splitting field for x cubed minus 2, because if this thing factors entirely into linear polynomials, then we're done. We don't need to extend the thing. But you see pretty quickly that that's not the case, because the graph of the function x cubed minus 2 as a function of real numbers, so this is x and then this is x cubed minus 2, that graph is going to look like this. It's going to have a vertical intercept of negative 2, and it's strictly increasing the whole way. So you see pretty quickly that you're only going to have one root for this polynomial over r. We're going to have to extend to get the other ones. Okay, so what are we going to extend by? Well, there's a couple of ways that we can approach that question. One way is just start factoring x cubed minus 2 over r and see what we get, and see if that gives us a clue about what we need to extend with. So over r, we have, and it's going to be kind of boring, it's going to be the same factorization we got before when we were in Q adjoin the cube root of 2, because that was all we needed to start factoring. P of x equals x minus cube root of 2 times x squared plus cube root of 2x plus cube root of 4. So that was a factorization. And then the second factor is going to be irreducible. And you know it's going to be irreducible over r, because if you use the quadratic formula, you find the roots do not live in r. Or you could just use the discriminant. You could actually square this, subtract 4 times 1 times the cube root of 4, and see that you get something less than 0. Okay, So anyway, we need to extend by something in order to capture the two roots of this polynomial. But what if instead of adjoining one of the actual roots, like cube root of 2 cis of 2 pi over 3, that would be the same thing we did before. Boring. So what if instead we reason like this? We say, well, we know this polynomial does not split over R, but we know that by the fundamental theorem of algebra, which we learned about a long time ago, we haven't proven it in this course yet, but it's probably something you've heard of. Every polynomial splits completely over the complex numbers. The complex numbers are kind of outrageously powerful. It's a large enough field to split everything, every polynomial having complex coefficients, which this certainly qualifies. So what if I just did this? Consider the extension field R adjoin, sorry, that should be parentheses, R adjoin I, which is really just the field of complex numbers. This is a degree 2 extension, because what I'm really doing is I'm adjoining a root of the polynomial, sorry, just a second, a root of x squared plus 1, which probably seems to have nothing to do with x cubed minus 2. But that gets me into the complex numbers, which is big enough to split this polynomial. So I claim that this is a splitting field. The only other thing I need to show to prove that it's a splitting field is to show that it is the smallest extension of R that is large enough to split this entire polynomial. But I can prove that in the following kind of unclever, inelegant way. So to show that this is the smallest that contains all of the roots of p of x, I'm going to actually go ahead and figure out what those roots of p of x are. In particular, I'm going to figure out this one, cube root of 2 cis of 2 pi over 3. Well, cis of 2 pi over 3, that is negative 1/2 plus root 3 over 2i, because I'm just literally taking cosine of 2 pi over 3 plus I sine 2 pi over 3. Those are those special values, negative 1/2 and root 3 over 2. Okay, so I've got this ugly looking number here. I'm just going to go ahead and simplify a bit so I can make the point that I want to make here. So that looks like plus square root of 3 times cube root of 2. I see no really elegant way of simplifying that. I could make all of that 1/6 root, but you're not going to like it, so I'm not going to do it. All right, so I have that. I have to have that in my splitting field. But, well, if I'm starting over R, then I already have this number. I already have all the real numbers. So I've already got this. So if my splitting field is going to have this number, this whole thing here, and it's also going to have this real part, then it must have this thing. And then once I have that, and I know that I have all the real numbers, I'm also going to have that times 2 over square root of 3 cube root of 2, which means that once I've committed to having this number and this whole number, I'm stuck having I, which means that extending by I is not only sufficient but necessary. So that's how I know that C is the smallest extension field of R over which P of X will split. Okay, so here my splitting field has degree 2 over the original base field, but over here when I started in the rational numbers, I started in the rationals, that first extension field had degree 3, and I'm just going to mark this in here. My new extension field, I didn't say this earlier, but it contains the cube root of 2 and this other root, which was a root of an irreducible polynomial. Sorry, this is a little bit crowded here. But it was a root of the irreducible polynomial x squared plus cube root of 2x plus cube root of 4, which was irreducible over this extension field, and it had degree 2. So that extension has degree 2 over q adjoin cube root of 2, which means that altogether, as we will show shortly, this extension here, my splitting field, has degree 6 over the original field. So the moral of the story is, when I was starting in Q, and I started with this polynomial x cubed minus 2, let's zoom a little bit, there we go. So I wanted to split the polynomial x cubed minus 2. I needed a field extension of degree 6 altogether over the original field. But when I started over the real numbers, or over the real field, and I wanted to split x cubed minus 2, all that I needed was an extension of degree 2, because the complex field is an extension of degree 2 over R. It's just extending by a root of this polynomial here, which is quadratic. So moral of the story is, when you talk about a splitting field or the degree of the splitting field of a polynomial, base field matters. We'll see more about these in a later video.